So first of all, thanks the organization of the conference. It's I guess it's a very nice. It's been a very nice conference, and thanks for letting me the opportunity to speak about this topic. So unfortunately, some people have listened to kind of similar talk. I changed the title from other times, but for the people that doesn't know anything about this topic, I will go very slowly with the topic, the introduction, motivation, and at the very end, some results. So I'm gonna basically discuss some results contained in this paper, but as I'm warning you, these results will appear at the very end. So my main, most of the time will be spent in introduction to the topic that basically is very much related with the Morse-Sar theorem. But the Morse-Sar result is maybe very well known in finite dimensions. So there is a motivation behind this paper and others that is try to extend the Morse-Sar result in infinite dimensions. So this is one of the main motivations about this work. And then, well, after I have introduced the Morse-Sar result, then I will go for the results and maybe some of the ideas and tools behind the proofs. Okay, so in general, okay, I will work with functions that act between Banach spaces, and I will work with the derivative of a function. So I'm defining here what is Frechet differentiable for a function at a point x. Well, here is the definition of the Frechet derivative. What I need to work with is with critical points and critical values. So for me, a critical point is just a point where this differential, which is a continuous linear operator between E and F, is not surjective. And the image of the set of critical points for me is the set of critical values. So the Morse-Sar result and also the results that I will talk about is about, do we know something about the set of critical values? So critical values normally is a bad set. We want to remove this set, no? Because then the level sets will be smooth somehow. No? If we don't imagine that you don't have any critical values. No? This is very nice. So what is the beginning of all of this? So maybe I hope that for most of you this is classical in analysis, but let's see this. So the beginning is with functions between finite dimensional Banach spaces, Rn and Rn. And we want to study the set of critical points of these functions or the set of critical values. And all of this started with this striking example of Whitney in 1935. I guess this is the beginning. Why? Well, he was able to build a weird function. To do that, by the way, he was using a very strong result nowadays, which is the C1, well, the Whitney extension result that he proved one year earlier. I'm not sure if he proved the extension result to build this example. I don't know. I have no idea. But it was helpful to actually build a function. Let's go for the example from R2 to R, which is of class C1 and whose set of critical values is positive. Okay, here, well, function from R2 to R, we can call the set of critical points just the points where the gradient is zero in this situation. Why this was weird? Okay, the point is that the function f there was a set, so a curve, where the function f, which is C1, okay, has vanishing derivative everywhere along the curve. So normally our intuition tells us, okay, if I have a function which is regular, it is C1, and I have a curve where the derivative is zero everywhere, the function should be constant in that set. The point is that, well, the image of that set of points, so that set of points, of course, is included in the set of critical points, gives you the whole unit interval 0, 1, so it has positive measure in particular. Okay, this was, at the beginning, weird, because what I'm telling you, if the curve was rectifiable, this is impossible, because you can use the fundamental theorem of calculus. The point is that in Whitney's example, he was actually building a non-rectifiable curve using a fractal, and he was actually making up all of this happen by force somehow. But the curve cannot be rectifiable. So why this is happening? Okay, so a few years later, there was an answer to this problem. And the answer is that if you give more regularity to your function, the previous example cannot happen. And this is the precise result that Morse and Sard gave in 1939, 1942. So actually, Morse first proved this result for real value functions, and Sard generalized this for vector value functions. So they proved that if you have enough regularity in a function, so if it is Ck with k big enough, it depends on the dimensions of your spaces, Rn and Rn, then you know that a set of critical values cannot be very big. which is the bad situation. So in particular, the Lebesgue measure of the set of critical values has to be 0. Of course, the point here, and if you think again back to the Whitney counterexample in 1935, is that you are not asking in Whitney's example, you are asking just for C1, but here your dimensions is n equal 2, n equal 1, and of course you are not reaching the enough regularity for your function to avoid that the set of critical values has measure 0. So that's what is going on. Okay, there are a lot of papers citing this result of SART, so it appears in many places in analysis. That's the reason why this result has been generalized to other contexts. What do I mean? Okay, one can ask the functions, instead of being ck minus 1, 1. Okay, so the last k minus 1, so the derivatives of order k minus 1 has to be Lipschitz, and you can get the same conclusion. You can extend it in some situations to Sobolev spaces, to spaces of bounded variation. So it is natural to ask, okay, do we have a version of the Morse-Sar result in infinite dimensions? So this was the motivation. So to put it in a different words, so if we know that a function between an infinite dimensional Banach space into another infinite dimensional Banach space or into R is very regular, very smooth, do we know that the set of critical values has to be small? This is the question. There were some tries, okay, to have a good version of the Morse-Sar result. I cite very quickly here Smale, who actually have a version of the Morse-Sar result in infinite dimensions, but he was giving, in my opinion, well, he was giving too many assumptions in the Banach spaces for this to happen. Okay, so your function has to be ck, and the derivatives has to be Fredholm operators, and well, I'm not going into the details of a Smale result. But for me, the important thing is that the quick answer for the question, does there exist a good version of the Morse-Sar result in infinite dimensions, is no. Okay, so Kupka in 1965 directly built a very smooth function, f, from the separable Hilbert space into R, whose set of critical values contain intervals, so has positiveness. So this is the direct answer. I am providing here another example that came in 2001 in some work of Bates and Moreira. They gave a very easy example, actually a polynomial of degree 3, where this was happening. So you can compute, this is an exercise, you can compute the set of critical points, and the image of that is the whole interval 0, 1. So we cannot expect to have good versions of the Morse-Sar theorem in infinite dimensions. So this is why we look for what we will call approximate Morse-Sar results. So even though there exists not a good version of the Morse-Sar result happening in infinite dimensions, one can still get the following. Let's read it. If you start with any continuous function from, again, the separable Hilbert space L2 into R, and you are given a positive function, epsilon, what you can do, first of all, Els and McAlpin in 1968, prove that there exists an approximation, G, very regular, C infinity, very close to F, which has set of critical values of Lebesgue measure 0. Even stronger. In 2004, Azagra and Cepedillo proved that you can get an approximation of F by a function of class C infinity, which actually has no critical points. And this is very strong. After this result appeared, there have been generalizations of this situation, because for Azagra and Cepedillo, they only proved this for this case. Here, they wrote the separable Hilbert space, L2. So there are other results extending this result, but let's comment only about this one. Azagra, Jiménez, Sevilla, 2007, proved the strongest possible version of this type of result. Why? Because they only assume E to have smooth partitions of unity of class C1. So they were only assuming E to have a separable dual. And if you know that, well, in this situation, you know that E has C1 smooth partitions of unity, so it's the minimum condition that you need to approximate continuous functions by C1 functions. Okay, so in that situation, they actually approximate continuous functions by C1 functions, and this C1 function has no critical point. Okay, there were other generalizations of this result, but now the target space could be a Banach space itself. Okay, so here I wrote a statement that was a joint work with Azagra and Dobrowolski. We were able to extend these previous results to, as I'm telling you, other Banach spaces as target spaces. Of course, in this situation, you need to work with some F here for which there exists surjective operators from E into F, because our goal is to not have critical points, so we need surjective operators. We need to work with F and quotient of E, but you can get, for many situations, so here I have just enumerated the classical spaces C0, LP, big LP, you can again get the same result, that all derivatives of these approximations are surjective linear operators. Well, the class of the smoothness of the approximation depends basically on the smoothness of the space E, of the Banach space E. Okay, just one remark. All of these spaces or all of these situations were for separable Banach spaces E. Again, well, maybe you have already noticed this, but all of these type of statements, of course, are false in finite dimensions. Just to make sure that you see this, I've provided here a very easy example. This is impossible to get in finite dimensions. Imagine I give you the absolute value function from function f from R into R. And I tell you, okay, approximate it by a C1 function without any critical point. This is impossible. You can, if it is a C1 function, you need to reach zero derivative at some point. You have the mean value theorem, you have the Rolle's theorem, whatever you want to call this. The point is that in infinite dimensions, the Rolle's theorem fails. This is the main issue here. It's very much related. So in infinite dimensions, actually, whenever you have a Banach space for which you are able to build a C1 smooth bump, you can build another C1 smooth bump, but now inside the support of this bump, all the derivatives are not zero. So you can avoid reaching the zero derivative because you get lost into the infinite dimensions. So you can have this completely non-finite dimensional results in these situations, okay? So what's next? Well, and now I go for the last motivation that we had for this last paper that we published last year was, okay, nothing has been done in non-separable Banach spaces, so at least let's write proof for the non-separable situation. At least the non-separable Hilbert space was open still. But of course we thought, okay, if we are able to play with separable Banach spaces and get rid of critical points for non-separable Banach spaces, everything should be, I don't know if easy, but we hoped that it was true still for non-separable Banach spaces that were smooth enough. And the answer is that yes. So one can prove, for instance, this result that I state here. So now we work with an arbitrary infinite set gamma, and let's think about these classical Banach spaces, C0 or LP. Then if you put f to be any quotient of E and you are given any continuous function f and any positive epsilon, then there exists a CK mapping approximating f so that all the derivatives are surjective linear operators. So there are no critical points. Again, K depends on the smoothness of the space that you are working on. For instance, in C0, you can get C infinity. Well, I recall here definition of C0 of gamma, LP of gamma, other versions. Okay, there are more technical versions that we include in that paper, but I will only state one of them, maybe one of the strongest one. I don't know, well, it depends on what you prefer, but if you have a Banach space with a C1 partitions of unity, again, this is the minimum requirement that I need to start with, because I am first of all, I am approximating continuous functions by smooth functions C1. So if you have a Banach space with C1 partitions of unity, and you assume, moreover, that E contains an infinite dimensional separable complemented subspace, unfortunately, this doesn't always happen. Why I'm telling this? Because if we are able to remove any assumption apart from this one, we would get the strongest possible result that we could aim for in all of this theory. But okay, we need to assume more things. So in this case, as I'm telling you, infinite dimensional separable complemented subspace. Then again, any continuous function f can be approximated by a C1 mapping without critical points. Another point here is that we need to work with finite dimensional target space. So it was not, we couldn't write here any quotient of E. So this is another point to maybe improve if one wants to improve more these results. Okay. So I have, I think, 5 minutes, if I'm not wrong. So I think I have enough time to just give you the very rough idea of what's going on behind. So the idea is kind of simple somehow, but then you find difficulties. Simple, why? Because of course, the way to approximate a continuous function by a smooth function is to use partitions of unity. because you know that you have smooth bumps. Okay, so this is the main point. So for the case of C0, let's look at C0. You directly have an explicit construction of the approximating function g. It's just through these partitions of unity. And the main point here is that C0 is very good space for us. Why? We need to study the set of critical points now of G. So we need to differentiate G, and we need to understand what is behind the derivatives of these bump functions. So this is the difficult part. We need to have an idea of how to derivate these bumps. So we need to know something about the bumps. In particular, for C0, it's good that we have partitions of unity that basically the bumps depend locally on finitely many coordinates. So this is telling us that when you derivate one of these ones, basically only a finite number of these E stars or the functions associated to the canonical basis of C0 appear. And this is very good because then you say, okay, take T, any surjective operator that you know that exists, but since C0 can be decomposed into infinitely many copies of itself, build actually an extreme surjective operator. So the T is actually surjective in every copy that you create of C0 of gamma. So it's time you restrict to this one of these copies gamma n, where you are dividing your set gamma of indices. T restricted to this complemented subspace in the big one is surjective. When you derivate your function, so when you look, well, that the function g approximates f is easy to check according to this definition, but this T that you write here, now when you derivate, if you go to see what is going on with the derivatives, the T operator appears, and then something that will only live in the span of the E star gammas. And since T was extremely surjective, somehow at the very end, of course, dg of x is surjective still. Okay? You don't care about this. At the end, L only is a finite number, a linear combination of finite number of these E stars gamma. Okay? So this finite number of E star gammas will, of course, leave out some of these other big gammas sub n. Okay? This is enough to know that this is surjective. LP of gamma requires more effort. The idea at the beginning is similar. You need to work with smooth partitions of unity. The point here is that, of course, in this situation, you don't know that the smooth bumps actually depend on finitely many coordinates, but it's not too bad to know that it also could depend on the norm of the space LP. So now the difficulty appears because you also need to derivate the norm. Okay? Why you can get this type of partitions of unity in LP of gamma? Well, we need to go back to the pioneering result of Torunchik, 1973, about the existence of smooth partitions of unity, using that you can embed LP of gamma into some C0 of gamma prime, whose coordinate functions are of class Ck. But using that, you can get this type of bumps, and you can differentiate. The problem for LP is that in this first approximation that I call P, I still don't call this PG because I still need to do a second step. The problem is that there could exist some critical points. So a second step in this situation is to get rid of this set of critical points that the function P could have by building a CK diffeomorphism H from E into E minus CP. If you are able to do that, and the function H, apart from being CK diffeomorphism, is not moving too much the points, this composition preserves the approximation to the function f, okay? And when you derivate, you look at the expression of the derivative, actually h of x, h sends any point x to something that is not a critical point. So this is surjective here. And this is isomorphism because you have a diffeomorphism. So you have a surjective operator. So this is the main trick. So I'm running out of time just to tell you that actually probably the most technical tool in all of this, or one of the most technical tools basically, is to diffeomorphically extract closed sets. So this is also called negligibility theory. I have stated here some results in the literature. Again, these results, if you think about finite dimensions, are impossible. Okay, I will finish with Besaga, maybe first result about this. He first proved something striking, that you can remove the 0 point and get a C-infinity diffeomorphism. Okay, of course, in Rn it's impossible. I don't have time, but this theory is necessary because you need to get rid of something that appears. Well, this is the final open question that we would like. Okay, what is the final goal in all of this? Again, only assume C1 smooth partitions of unity. But this is difficult. At least with our techniques, we find this difficult. So we don't know still. If you want to know, I'm not thinking about this question anymore. I have moved to other questions, but I would say that this is, since I think it's difficult, I'm not thinking about this anymore. Thank you.